Azzouz from Beijing Institute of Mathematical Sciences and Applications. I will talk about p-adic linear differential equations.
And first, thank you for the invitation. And today we'll talk about p-adic linear differential equation. But what we mean by p-adic is just we will consider a field of number which looks like the real number, but it is not real number. Just recall that if we have a real number, then we can write it using the decimal way by a sum, by a finite sum. With here, the index is positive, and here AI is an element from 0 to 9. And there exists, and there is the other side, which is behind the dot, when we write our real number using the decimal form. It is an infinite sum, and yes, and the coefficient here are also in between 0 and 9. Then we can do the same thing with the p-adic number, but just be careful. And yes, because this we will see that we can define an absolute value, but that correspond to our prime number. Then we have a prime number. Then what is a p-adic number? Then it is something that we can write in this way, and the coefficient here will be from 0 to p minus 1. But the difference is that compared to the real number, here the power, the index of positive power are the sum where the index of where the power index is positive. It's not a finite sum, and where the power index is negative, the sum is finite. Then the set of such element is called the p-adic number, and we denote it by QP. And what is an p-adic integers is just we suppress this part. And sorry, here is here it consider rational numbers, and just the real number is just the completion of rational number, and it is the same here. When the coefficient here are equal to 0, then we have integers here, and we have the same idea for p-adic numbers, and we denote it by ZP. Then the operation of addition and multiplication, we use the same algorithm, which means that we can be defined in some sense in the same way as for real number or rational number or all these things. And
I mean, can I interrupt you for a moment?
Yeah.
Yeah. Is it trivial that the sum converges so pi is
no. The thing is that we defined it like that. Let's say it's a formal power series, but yes, there is another way. If we start by defining by just considering the absolute value, and then we consider the completion with this absolute value, and yeah, for this, for example, for this absolute value, the absolute value of p is strictly less than 1, and then that's what make it converge. But we can define it using a formal way, just it's a formal series, and then we define the absolute value, and when in the end we find the same thing. This is just to make things just easy to understand. But yes, we can start by this is complicated way how to fit sophisticated way how to define it, but it is yes, you start by a rational number, then we define the p-adic absolute value, then we complete with this absolute value, and then we recover the same thing.
Okay, so the point is that this is a formal definition, just to make it
yeah, it's a formal definition.
Okay, thank you.
And And yes, and any element using this definition will admit an opposite, and if it is non-zero, it admits also an inverse. For example, if we here just look here. Here there is no negative number. However, for example, if we want to have the opposite of one, which is the opposite with respect to the addition, then we can express it in this way, and formally it is something that it corresponds to this power series. And also for the inverse of, I just give an example of an inverse of an element, then this one, it can be expressed like something like that. Therefore, we have Z, which is including ZP, and Q is as a ring. We can consider it as a subset of ZP, and and Q, the rational numbers is a subset of QP. Then here, this is just, we start by defining it using formal power series, and then we can deduce that we have this condition. We can do the reverse. We start by this and then define the absolute value, and then we recover the series. But they are in some sense the same. Then on this on QP, we can define an absolute value. And the idea of this absolute value is that two numbers are too close if they are, the difference between the two is divided by a high power series, high power of P, sorry. And yeah, we can, and then we can define it in this way. If we have a series, then the absolute value is P power minus the valuation of X, and this is just the minimum where this coefficient is not equal to 0. Fortunately, remember that over real numbers, there is some polynomial that they don't have roots. For example, the polynomial with discriminant strictly less with negative discriminant. In that situation, the polynomial don't have roots in R. Then we know that if we look at higher extension, which is C, then everything, all polynomial have a solution. There exists the same problem over QP, and to resolve this, then there exists also an analogous of C, which is called CP. Then there is something just to be careful. CP is not a finite. It's not an algebraic extension of QP, but it is algebraically close, which means that any polynomial has all its root on CP, and it is complete. However, the algebraic closure of QP, it's not complete. Then CP is just the completion of the algebraic closure of QP. Yeah. Then for the rest, we will consider the number over CP. Yes, this make think more simple for our talk. We will not, because just to avoid the definition of ultrametric field, general ultrametric field. Then, for example, if we take P to be the prime number 3, then Q3 is, let's say that if we look to all the disk, if you look to the disk, the unit disk, then this one is just it's just a disjoint union of 3 smaller disks, and yes, and each one we will have when we want to recover all the number of Z3, then they are distributed like that, and we start by 0, and here it's just something that the number here will start by something multiplied by 3, and I add all the power series. And here is the same, is something 1 plus, and then I can, I mean, the difference between all this, the number that they are here is divisible by 3. And here is the same, the difference, any number that they are here, they are divided by 3 power 2, and so on. And we can do it for each power of p. And we can see that they are divided into disjoint disk, and for each number, it's two number can be separated always by open disk. This is just an example, but more generally, when we consider the p-adic absolute value, there is something strange about this this absolute value, is that when I define the distance, which is defined by this value, then all the open disks are in the same time closed, and all the closed disks are in the same time open. Unfortunately, this implies that CP and QP are totally disconnected with respect to this distance, which means it cannot be connected. I cannot connect to 2 points. This is really inconvenient because, for example, when we want to define an analytic function, then remember over complex fields, if I have two functions that they are equal into an infinite set, let's say, and they are all defined on a convex part, then it means that they are equal. Then here it's not, we cannot say such a thing, but we'll see that we can resolve this problem later. Then there is something strange also, is that if we have, and every triangle is at least isosceles, which means that if I have 3 points, there it is at least 1 point that it is equidistant to the other point. And this implies that this we cannot imagine in real life, that any disk, any element of the disk is the center of the disk. But hopefully there is something that it is nice about ultrametric, about this absolute value, is that in the situation of if I have this one converge to 0, then I can conclude that this one converge, which is not the case for a real number, for example. We may have something like that, but this doesn't mean that we have the convergence here. Now we can talk about p-adic linear differential equation. The thing is the following. Since we have defined our numbers, it's a field, there is a addition, multiplication, and there is an absolute value, then we can easily define the notion of power series. It's just a sum, and we have the coefficient which they are in CP, and we have the indeterminate, which is T, and we can say that we see the over a disk, then we can say that it is converge if and only if it is the same condition. We just use the absolute value, and then we obtain what we want. There is no problem about that. Then what is naively what is a p-adic linear differential equation? Then if we define power series, then we have the indeterminate. Then we can consider the derivative with respect to this indeterminate, which is we will call t, for example. Then we can consider derivation d over dt. Then we can define the derivative of the function. And p-adic naive differential equation is something that we consider it's an equation like that. And here the coefficient are locally power series with coefficient in CP. More generally, we can generalize this notion by just using a linear system, and just here any matrix with coefficient where the coefficient are local power series, we can define a linear system. However, there is something that we need to be careful. When we, for example, when we are over C, and just let's say we consider an open disk over C, then any differential equation that it is defined over D admits all its solution, which means what I mean by all its solution, that just for example here, yeah, the matrix here is n time n. In such kind of system, then the solution should be a vector space, a CP vector space, let's say, and the dimension should be n, which means there exists at most n linear and independent CP linear and independent solution. Here is just mean when I say all its solution, it means that the dimension of the solution is exactly equal to n. And there is no problem about it will converge on the whole disk, the solution. However, in the p-adic setting, if we consider, for example, just if we consider the simple case where this one, we usually over R is just the exponential. Over p-adic number, exponential makes sense because all this yes, we can define it formally, and this makes sense because Z is included in CP. And however, this one cannot converge on here, since it is supposed to be defined on over all CP. And we hope that the solution will converge on all CP. And and this was supposed to have a radius of convergence that it is equal to infinity, but unfortunately this is not the case, and this is just because here, let's say, I didn't say it before, but we can deduce it easily. All integers or p-adic integers has an absolute value that it is less or equal to 1, which means if I take the inverse, then it is something that it is greater or equal to 1. And then we cannot obtain an infinite radius of convergence. And more precisely, the radius of convergence is equal to this value. There is also something strange about in the p-adic setting. Then the radius of convergence cannot be maximal. And the thing is that if I change the point continuously, let's say, if I change the point first, if I change the point, then the radius of convergence is it's not necessarily the same. Hopefully, in this situation, it is the same, but in general, it's not the same. Even if they doesn't make sense to say they are in the same connex, but later we will see even if they are when we will resolve the problem of the discontinuity, even if they are in the same connex, then it is not necessarily that the radius of convergence is the same. And how the theory of p-adic differential equation developed, let me say some history. Then this topic became very interesting, gained interest since the work of Dwork in 1960, when he proved the rationality of the zeta function of a variety of positive characteristics. Then, after this work, then there was a series of work of Dwork and Roba where they develop more this theory. And in the beginning, it was over the affine line, but at that moment, they were using more functional analysis to define affine line. It's not like I will explain now, where we can use a geometric notion and explain what is the affine line. And after that, this theory was developed over some other ring, Roba ring, which is some kind of ring of special analytic function, and this one, the differential equation over this ring is related to the then yes, what I mean by global theory, for example, if I have some point and I want to look to the differential equation over this point, makes sense, and it makes sense also to look how it behaves in a neighborhood of this point. That in some sense, maybe. Then let's say, first, talk about the pioneer work of Dwork and Roba, which was I just explained. It was started from 1980. Then I said they developed this theory and they introduced several K notion. For example, the overconvergence, the Frobenius structure, which is something that we can define over differential equation and give us very make things more easier to have some property, solvability. This is some problem about the radius of convergence and the equation, and we can this is something really interesting. Why? Decomposition by the radius of convergence. In the complex case, as I said, it's something the radius of convergence is something really trivial. Then we cannot do it. It's just something that belong. If I have a differential equation defined over disk, it will be just the radius of the disk. If I have, for example, a disk for which I take a finite number of disks, then it is something. It's an invariant that it is just related to the geometric. To the geometry of the domain where the equation is defined. However, in the p-adic case, it's something that it is really related to the equation, not only to the domain. And we can decompose with respect to this radius of convergence. I will explain later what we really mean by that. And there is something interesting when we study the behavior of and how the radius of convergence vary. It has a link with the Rham cohomology. And this influenced a large part of literature. Several authors have pursued an agenda of analysis whose aim was to prove the following important relation. As I said, the decomposition with respect to the radius of convergence. But in the beginning, this one was only in some special case, but this was generalized in more and more that I will explain later. And this one is also something that it is correspond with the cohomology. Then, in order to study ultrametric differential equation, it's really important to describe the underlying geometric space. This is not strange because, for example, in the complex case, when we want to compute, let's say, the primitive of a function, of a holomorphic function, that the knowledge of the geometry of the space is really important. For example, if we consider the primitive of 1 over t, since it is not defined on 0, then the primitive doesn't exist. And we have, for example, the result that say if we add the domain is simply connected, then any function admits a primitive. Then that's why in substance it is important to understand the geometry of the space. For that, and since the p-adic field, we cannot do the same because it will make no sense because it is totally disconnected. How to say it? If we want to define an analytic function in the same way in the complex case, then it will make no sense. That's why several languages can be used to define nice space, let's say. For example, there is state, there is Huber language, and there is the Berkovich one. Then in our study, we found out that the p-adic language is the more suitable, and this is because it is really the main characteristic of these spaces. So are very nice topological space, and in some sense we can define. We can have the same reflex as in complex geometry. For example, the topology of such spaces are locally compact and they are locally path connected. Yeah. Then let's just give a picture about how such space looks like. Then the idea of such space that we have all the points that belong to CP, and for each, we will say just for the moment, I will give this definition in some sense, which is more easier, but later I will explain more from where this point come out. Then let's start. We have the point that belong to CP, which are, we will say that they are point of type 1. Then for each disk, I mean for all, then each disk which correspond to a center and already, let's say we add a point. And for example, and for each disk we add a point. Then remember, I told you before, if two disks, if one disk contains 2 points, then each of this point is the center of this disk. Then, for example, if I have a point here and a point here, then the disk with center C1 and this radius, close the disk here, it corresponds to close the disk, not only open. Then this disk contains both points, which means C4 and C1 both are the center of this disk, which means that this point, any branch will meet the other branch at this point, and then we can in some sense glue all this point that they are in CP by such a line, and then in the end we will recover an infinite tree, and this tree is before going so far, just yes, we talk about this, but there is some point that they are here. There is something particular also about CP, which is not the case for C and not the case for R. In CP, we may find something that it is strange, that we have, let's say this one correspond to disk. There they have their center somewhere here. And if I consider all the intersection of this disk, unfortunately, it may have an empty, it can be empty, which means in some sense there exists a closed disk which is missing. Then let's say that this point where it represents this disk. And here is just if R it may exist some value in R for which there is no element in CP that have absolute value that it is equal to R. Then if R is such a R, then the only point that is glued to this point is the point C here. There is no other point that can be glued here. This is just let's say a small picture of the analytic line. Okay, more precisely, it is the closed disk of with center C1 and radius, which is equal to this value. But the difference, as I said, if R is not here, the value, the group of absolute value is not here, then there is no point that it is linked to here, and you have something like that. However, in this case, then it should be glued with point that they are here. Then what is the open disk? It's just I take off this point and all the points that they are belonging here. In this case, since there is no point, it's just I will remove this point. And yes, this is the open disk. A connected affine domain is just something. It's just a closed disk for which I will remove a finite number of open disks. And in the case where I will remove only one, then yeah, this one is the open. That's it to see it well. If I take off a disk here and then each here there is many disks. That's why for the analogous open one, then it is just we have a branch here, and for each point there is we glue other open disk in the whole Nile. We can see it like that, or we can see it just like that, and we remove only one disk. There is also a point that, yeah, here also, if we take off this point from here, then it will be a discontinuum of open disk. Yeah, that's what I mean here. As in analytic function on affine domain, or in closed disk, is just something that it should satisfy. They are power series that they are satisfying such a thing. Yeah, this is a nice picture of what could be the affine line. It's something that it is an affine tree. This is just, and the projective the projective Berkovich line is just I will add the infinity, and then I have something like that. For analytic curve, I will just explain something. Contrary to for example, to the complex case or the real case, or in differential geometry, when we have and we want to define the curve locally, it's just something that it is locally isomorphic to a part of C, or yeah, an open of C, let's say. But for example, here in the p-adic setting, it is not really the case, but hopefully it is almost the case for if I consider a curve. I cannot give the definition, but I will just explain how it will looks like. Then, except a locally finite number of point of type 2 or 3, then everything is isomorphic in some sense to a part of the affine line, which means there exists only locally finite. If I take off this all point, then I will find, for example, an analogous here, the same thing for here, and here, for example, it will be an open disk, here an analogous, and so on. Then what is a differential equation over a quasi-smooth curve? Let's say, rudely speaking, then around each point, and be careful, around each point of here on the curve, not only the point that they belong to CP. I can define differential equation of this kind. Really, what I mean by that is just if I have a point X, then I can choose a neighborhood, and then choosing an analytic function on this neighborhood, then I can define the differential equation. But for example, to say the solution around X, then we need to explain more. It's not quite obvious how it behaves. Then the thing is that if X is not belonging to CP, for example, then there is a way to make it in some sense like that. It's just by considering an extension of CP, which is complete, and for which the p-adic absolute value extend to this field. Yeah, I said CP is algebraically closed, but here the extension is not an algebraic extension. Just we need to be careful about that. It's just an extension, and I will explain why such a thing exists in the p-adic setting. And then, in some sense, I can make this point X belonging to this field, and then this point will be belonging to our field, and then it will make sense to look to the powers to the solution of the equation around this point. Just to take the Taylor expansion with respect to this point, and then we can compute the radius of convergence of this equation. Yes, really speaking, there's two situations. We have our point here. Then when I extend the scalar, let's say we use this, I use a higher extension for which I can make this point a point of the field. Then in some sense, my curve will be something like that, or it can be, there is two situations. There is the first situation where this point doesn't admit an open disk as a neighborhood, and there is this situation where my point admits this the disk as a neighborhood. Then when I do an extension, then this disk that as they are in this picture, there is then I can consider my point on this disk, or there is a situation where this disk all belong to the bigger disk. Then when I will look to the solution around Tx, there is two kinds of radius of convergence. Then the first kind where I will consider that the solution converge, I will just look where when they converge only on the blue disk, and this kind of radius of convergence we call spectral one. And there is the other situation where I will look to the solution on the whole disk where my point is, where my point belongs. What is the difference? For example, if I have a solution which converges on a bigger disk, then just the spectral radius which correspond to this solution will be just truncated at Rx. There is a difference between these two radius of convergence that I will explain here. Yeah, as I said, the radius of convergence is not a trivial notion. It's a very important invariant. And the radius of convergence, which they are on this disk, not only inside this disk, then they are continuous on where my differential equation is defined. However, if I consider the spectral one, then it is not it is continuous, but if I consider a point, then it is continuous only on finite graph. For each point, each finite graph. In each finite graph, it is continuous. But if I consider the whole topology, then I may have a problem. That is the difference between the two. However, the other one, in almost the case, it is the same as the radius of convergence. And there is a way using functional analysis how from the spectral radius of convergence, we can deduce the radius of convergence. That's why it is important. It is, yeah, I will explain it later. And more precisely, yeah, here the domain are R3, then it makes sense to talk about the log affine. Log affine is just in the logarithmic coordinate, it is affine function. And more precisely, and there is something that it is really nice about the radius of convergence. We know that they vary. However, they don't vary. Hopefully, they vary only on a locally finite graph. which means that if I take off this graph, outside this graph, then it is locally constant. When I remove this graph, it's from this curve, then this one will be addition to union of open disk. And over each disk, then it is constant. Then this information of this property of the radio of convergence give they permit to obtain several important information about the equation. Then the first one is that we can, as I said before, we can decompose with respect to the radio of convergence. Then we have a local decomposition in direct sum. This one, it's just concern the spectral one, spectral radio of convergence. If we, with respect to the spectral radio of convergence, we have a local decomposition in direct sum. However, if I consider the radio of convergence, there is some situation where we cannot decompose it in a direct sum, but we have an exact sequence, a global, we can obtain a global decomposition in an exact sequence. And in some condition on finiteness of, when we, if we have the information about this finite graph, we can give some condition about where we can deduce that we have the group of where the group of the Rham cohomology have a finite dimension. And the index of the equation, this is something that also it is related to the Rham cohomology. In the case where this one is finite, then the index can be obtained with respect to the irregularity of the radio of convergence. The irregularity, since they are not constant, there is something which let's say the coefficient of the slopes of that correspond to the radio of convergence will give us the irregularity of the equation. Then this is about the radio of convergence. This is work that has been done. Then we can now talk about what I do really in my research. Then we have seen that we have this real number that give us very nice important property about the differential equation. In my research, there's something that we call, this is just a picture about the controlling graph. Just before I show you that we can have a graph for which if I take it off, we have only open disk, then the controlling graph, it can be even bigger than this graph. It's just a picture. And to say just if I take off this graph, then the remaining will be constant. Then let's come back to what I was saying. Then there is something that for a differential equation, we can associate a geometric object, which is the aim of my research is to study this object and deduce from this geometric object a property about p-adic differential equation. It is called the spectrum. And which will be in some sense the spectrum associated to an operator associated to the differential equation. Then let's recall what I mean by the spectrum of an operator. Remember, for example, if we consider matrix, if we consider a matrix, then the spectrum of the matrix are the eigenvalue of this matrix. Then this notion can be generalized, and like just if you have an operator lambda, then the spectrum is just something. They are lambda which belong. For example, let's say we are in over an algebra, an operator, an algebra. Then the classical notion of the spectrum is just the lambda that belong to the field for which this one is not invertible. And this is generalized notion of eigenvalue. Then, for any operator that it is defined over a CP algebra, we can define the classical spectrum. However, this one is not very it like how to say, many information lake from this spectrum, and it doesn't have the nice property that we have, for example, for the complex case. I will explain it in more detail this part when I will finish, just because I will give just really speaking my result, then I will explain it more precisely what I mean by the spectrum in the sense of Berkovich. Then the idea of Berkovich, and it was his idea to define Berkovich spaces. His idea is to consider the set of the spectrum as a subset of the affine line, not only a subset of CP. And for any differential equation, we can define an operator, and this operator is just defined using this matrix. And one of my results is that when I compute the spectrum, then it is a discrete set, and there is an important part of this discrete set. This is just to translate. They will not give me more information. And the main idea is that for each point which belong here, then I can decompose. Here we can, doesn't make sense to say decompose, but yes, let's say that I can write, there exists a basis for which my system can be expressed in this way. Moreover, in my result, we can also link that this, this one is just correspond to the decomposition of differential equation. In the beginning, I said if I have different radius of convergence, then I can decompose. And the particularity when I use the spectrum, then this decomposition is finer than the one that we can find with respect to the radius of convergence.
So Tinhinane, maybe maybe we could stop for the first part, and you can continue in the
This is just the first part, and yes, and
okay.
I will continue.
Okay, thank you, Tinhinane.